start with calcium imaging, we need to prepare the sectioning chamber filled with room temperature NMDG ACSF, pH 7.4. All the solution used for calcium imaging need to be constantly carbogenated. Carbogen is 95% oxygen, 5% CO2. So you'll need to have the sectioning chamber ready, NMDG, a Petri dish with NMDG, and then a small container with NMDG at 34 degrees Celsius. The other thing that needs to be ready is a different container filled with holding ACSF. So holding ACSF is the second solution on the protocol, and it's just a buffered ACSF. This one too, constantly carbogenated. So we're going to prepare the sectioning block. This is just 3% agarose, and we cut a little cube with a razor blade. Pull it out, and we need to glue it to the sectioning disc. To do that, we use Loctite 495. Just a little bit. And then I try to clean up the excess of glue. When the animal is fully anesthetized, we will need to perfuse it with oxygenated NMDG. So what I do is filling a 16 milliliter syringe with about 25 milliliters of NMDG. And use a cut needle for the perfusion. After the perfusion, the brain needs to be extracted really quickly, put in the Petri dish with the NMDG, and then we need to create a flat surface to glue it to the sectioning disc. So today we're sectioning the PVN. So I'm gonna cut the cerebellum. At this point, you need to put a little bit of glue on the sectioning disc. And then with a spatula, grab the brain and delicately put on the disc against the agarose block, and then quickly in the sectioning chamber. Now we can start sectioning. In this vibratone, it's manual, to move the blade up and down. We'll have to turn this wheel. Each turn is 100 microns. So what we want to do is move the blade close to the brain. So I'm sending it down. And then with this knob, you can push the blade forward until you're next to the brain, and then you pause it with the pause switch. We're going to position the blade where we want to start sectioning. Cut off the forebrain, like regular sectioning, if you wanted to section the PVN. You can add a little bit of NMDG if it's not enough. I'm removing all the parts of the brain that I'm not interested in. Okay, we are right before the start of the PVN, so I'm going to start collecting. For calcium imaging, we need 300 micron thick sections, so 3 turns of the knob. 1, 2, and 3. And then you want a section with minimum speed and maximum amplitude. With the help of a soft brush, I collect the section and I transfer it to the warm NMDG. Section needs to stay in NMDG for 12 minutes. And then I just continue with the next section. It is very important that the section never leave the liquid, otherwise the cells will die and you won't see any activity. After 12 minutes, we need to move the section from the 34 degrees Celsius NMDG to the room temperature holding ACSF. So again, we're going to use a cut Pasteur pipette. We'll start with the first section, the most frontal one, and then slowly progress to the most caudal section. And I wait about 45 seconds between a section and another one, because that's what I estimate it takes to section it. So I move the section 45 seconds spaced apart. Alright, for the recording, you will have this setup. So you have your section in the holding ACSF. You have a bottle with a recording ACSF with the inlet pump from inside the bottle goes to the microscope, and then you have an outlet pump that goes from the microscope to the waste bottle. So we need to install the imaging chamber in the microscope. It's been designed to fit perfectly into this microscope. So the chamber goes here, we lock it in place. We connect the outlet pump here. This is just a needle with a bent tip, and this is a little bit of sticky thing. I don't know how it's called. So this goes in here. And then same thing for the inlet pump. Send the ACSF through the chambers and then out to the waste bottle. So we need to balance the speed of the two pumps to have a steady flow in the imaging chamber, so that it doesn't overflow or the section doesn't dry out. So you help the liquid with a brush. To set up the confocal from the Leica software, you need to set your acquisition mode to XYT, the speed to 600, the bidirectional X on, phase X minus 33, zoom factor X 0, and then click minimize. The frame rate should be 1 frame every 0.63 second, so about 2 Hertz. And then GCAM6 emits in the green range, so we're going to use the 488 laser, and usually about 30%. If you look at that, it seems that the two pumps are fairly balanced. There's enough liquid, it's not overflowing or running dry, so we can start. When you're ready to start, you're going to pick a section up and put it in the chamber. Then we're going to use a piece of metal to keep the section down and prevent it from moving. Now with the normal fluorescent microscope, we reach the area of interest. This time is the PVN. For the imaging, just a regular confocal imaging. So we might want to open the pinhole a little bit, See more cells, about 2. And then the cells that are very bright, usually they are dead. We're going to use them to calibrate the fluorescence. So we're going to increase the laser until these cells are burned out. So about here. And then you adjust the focus to capture the largest amount of cells. Let's say maybe here. I usually use a 1.5 zoom factor. Now we set the duration to 15 minutes and then we can start imaging. Near about a minute from the end, we need to stimulate the section with KCl. So with a pipette, you just slowly squirt KCl in the imaging chamber. And that should result in a cell activation. Okay, so you will have your video as a collection of TIFF files. So the first thing to do is stabilize the video with ImageJ. So we open ImageJ and we need to import the file into ImageJ. So import as image sequence. Then you'll find the folder with your video. Convert to 8-bit, so it needs to be converted to grayscale, and then OK. So to stabilize the video, you need to go in plugins, and then it's stack reg. Sometimes when you download ImageJ, stack reg is not a plugin that's in there, so you will need to download it. So you just click stack reg, don't mind this, and then transformation rigid body, and then click OK. It will take about 3 to 5 minutes depending on the length of the video. Now that the video is stabilized, we saved it in a folder on the desktop called MATLAB videos. We can open MATLAB. So the code is going to be on the left side here in this folder called ICA code 2. So you double click, and the script is this one with the longest name. So start it, double click it. So the script is in sections, and to advance through the sections, you use the run and advance button up here. So the first section is just to initialize the whole thing. So we click it, and here is where you put the path to the folder. So the folder is called MATLAB videos and it's on the desktop, and then you need to put the file name you're working on. So our file name is this one. So what you can do is just copy and paste it here in the script. And it's a TIFF. Now you can run and advance this section. This will open the ROI manager where you can select the cells that are firing that will be analyzed by the software. To identify the cells to be analyzed, the fastest way is to scroll down to the moment where you put the KCl, which is usually by the end. Here we can see very well this cell. So to select the cell, we circle it, and the software gives us a preview of the activity right here. The last peak is usually the KCl. For the sake of this video, we're only gonna do one cell. So don't close anything, just click back here in the script and run the next section. Usually when you click, it highlights the section after the one you're running. Some section take longer, some section take shorter. You know when it's done when the next section is highlighted. Whenever one section asks for a range, we need to pick the range from the first frame to the last frame before the KCl. So you go back to this window and you check what frame was the one before KCl. In this case is about 1400. You go back here and you put 1 to 1400 in the range, then you run it. So in this section, it will correct the slope of the whole thing. So simply, it's automatic. You simply run through all the cells pressing the space bar. So if you press the space bar, you see that the blue line is the original one, the green line is the normalized trace. So when it's done with all the cells, it will automatically highlight the next section. So this section is the most important one. This is where you manually select the threshold for the spikes. The first one is always blank. We click twice above the blue line, and then this is the first cell. In this case, it asks you for the horizontal threshold first, and I would put it right here. These are not real spikes, this is just noise. These are the real spikes. So the threshold must go here. And now ask for the vertical threshold, which is the KCL threshold, which means that you need to cut off everything that's KCL. So I would put it here. So we cut off the last spike, which is just KCL. There you go, and it's done. Keep advancing through all this section. They will prepare the data and everything for the analysis. This section, again, asks for a range. So we put the same range we put before. Again, there's a range. It calculates the number of events. Okay, so this part is where it starts saving Excel files with all the numbers we need. So the two that we actually need are the TE number, so the total event per cell, and we'll save it with the name of the video. So TE, this particular video is called CRH344, so we'll save it as CRH344. This section is not necessary, it says here in the script. So to skip a section, you just click on the next section, and then you run it. So EL is actually not necessary. What we need is AVEL, which is the average length of an event, so the average length of the calcium spike. So again, we change the file name to AVEL CRH344, and then we run it. These are the two pieces of data we need. So at this point, it's saved. You can see it's saved if you go back to the main MATLAB section, and here you should have your AVEL and your TE files. At this point, it's done. You have the total events and you have the average length of the events, which are the two pieces of data that we usually use to analyze calcium imaging. That's it.